Welcome back. We talked about exponential growth function in the past video. Now let's take a look at exponential decay function. Exponential decay means you're starting with a certain amount and it is decaying, means you're losing some amount from it, and at the end it's going away, right? It's diminishing in size and it's going away. Not totally, but it's there, but it's going away. All right, so you have this exponential decay function. I'm going to explain it using an example. There are a lot of things that happens in real world that can be modeled using an exponential decay function. For example, the half-life of a radioactive material or the strength of a radioactive material. The strength of the material keeps on decreasing over time depending on what the half-life is. We will discuss about this in class also. Any car value, if you're buying a car, a new car, over the year, the value of the car is going to depreciate and you're not going to be able to sell the car for the same price that you bought. So that could be an example of exponential decay function. The decay of an organic matter, meaning in real world you have dead and decaying matter. It could be an animal or it could be a tree. So that matter is decaying. That can be explained using exponential decay. Remember, they do carbon dating, right? The carbon dating is basically using your exponential function to figure out what the time is. All right, so any depreciation value, any depreciation of value problems, they can all be modeled using exponential decay function. All right, so here let's choose an example. So I'm going to use the car value. All right, so say you're purchasing a car for $20,000. all right, so you're purchasing a car for $20,000. That's the car value initially, right? Initially. And the value of the car is depreciating. Value is depreciating. Value is depreciating at the rate of 10% every year. This is just hypothetical, okay? I'm not saying it is depreciating. It's just a hypothetical problem that we are looking at. So I started off with the value of the car as 20,000. I took the car out of the showroom and the value starts depreciating immediately. All right, so the beginning of the time, I'm going to make a table again. All right, so this time my time is the number of years, my input is the number of years, and the output is the value of the car. What is the value of the car after a certain time has passed? All right, so the beginning of time, meaning I just took the car out of the showroom, the value of the car is $20,000. all right, the value is depreciating at the rate of 10% every year, right? So the beginning of the first year, it is 20,000, right? End of year one, what is the value of the car? I started with 20,000. Now it is reduced in price, right? How much has it reduced? It's reduced by 10% of its original value. So 10% of its original value is 20,000. Original value is 20,000. 10% of that 20,000. What is 10% of 20,000? So I'm going to do the calculation here down the bottom. 20,000, right? 10% of that, 10% is 0.1, right? So what is that? So that is 2,000. 2,000. So 2,000 is off its value. Now at the end of year one, the value of the car is 18,000. All right, so end of year one, the car value is 18,000. As you can see, the value is going down, right? So that's depreciation. So now beginning of year two, the value of the car is 18,000. So end of year two, another 10% has gone off. Now the 10% is calculated on what I started with in the beginning of my second year. So I started with 18,000. Now another 10% has gone off. So 10% of 18,000. 10% of 18,000 is 1,800. Right? 1 times 18,000 is 18,000. I have a decimal point. I'm going to keep that decimal point. That 0 goes away. So that's 1,800. So 18,000 minus 1,800. 18,000 minus 1,000, 17,000 minus 800 is 16,200. All right, 16,200. That's the value of the car at the end of year 2. Now beginning of year 3 is 16,200. End of year 2, the value of the car is 16,200. Beginning of year 3, it is 16,200. So end of year 3, 16,200 minus another 10% of this value now. So 10% of 16,200. 10% of that. 1 times 16,200 is 16,200. 1 decimal point that goes away. We got 1620. So I am taking away 1620 out of that value. So 16,000 minus 1,000 is 15,000. 15,000 minus, that is 15,200 minus 600 will be 14,600. 14,580. Hopefully I'm right. Okay, so let's check it with the calculator. 16,200 minus 1620. 14,580. So third year, 14,580. All right. So it keeps on going. I can keep on doing it, but I'm going to stop right now just to keep time in mind. All right. So here I have a function that's decreasing, but I'm not decreasing the same amount. So it's not a linear function. So it's not going down by the same amount. The first year it went down by $2,000. The second year it went down by $1,800. The third time it went down by 1620, because the value of the car at the beginning of each year is lower and lower every time, right? So a percentage of that is going to go down. So how much did it go down? What is the common ratio? So this is not a linear function because it is not going down by the same amount. All right. So I want to know what is the relationship, what is the pattern here? Does it have a common ratio? So again, it is y2 over y1. So 18,000 divided by 20,000 is 0.9. So 20,000 multiplied by 0.9 is going to give you 18,000. All right. So next, I want to see if it is a common ratio. So 16,200 divided by 18,000. Again, it is 0.9. So I am seeing a pattern which I like. 14,580 divided by 16,200 is again 0.9. So 16,200 multiplied by 0.9 is going to give you 14,580. All right. So just like we saw in our exponential growth function, if I want to write an equation for this, I start with f of x. I know this is an exponential function, exponential decay, because it is decreasing in value. So f of x equals a times b to the power of x. We know that this is a time function, so I'm going to change the x to a t. F of t equals a times b to the power of t. I start with an x because both are exponential, right? So I start with the standard equation of my exponential function, and I'm going to tailor it to my exponential decay. All right. So let's write a function for this specific situation. So I know here a is my initial value of the car, and b is how much is the ratio, the common ratio. All right. So if I want to write a function for this specific situation, I have f of t equals 20,000 is my initial value of the car times my common ratio is 0.9 to the power of t. All right. So this is the function of my car situation. All right. So how did we get there? So let's take a look at it. So 20,000 is your initial value. It is already given to you in the problem. So to calculate my common ratio, either I could make a table like this and then figure it out, do the long way and figure it out, or I have a shortcut that I can take. All right. So what is happening here? I had 100% of the car, which was $20,000, and I took away 10% of it because that's my rate of decrease. The rate of depreciation is 10% every year. So from that 100%, I'm taking away 10% every year, right? So 100% is a whole, which is 1. 10% is 0.1. 10% is 0.1 as a number. So 1 minus 0.1. This is my rate of depreciation, right? Rate of decay. So 1 minus 0.1 gave me that 0.9. So this 10% is given to you as a rate of decay, rate of depreciation or rate of decay, I call it. So B, I got 0.9. That's how I have that 0.9. So in general, in your problem, your initial value is given, your rate of depreciation is given. All they have to do is take that rate of depreciation, and I'm going to take it away from that 100%. So 1 minus 0.1, I'm going to change it into a number and then write it as a number because I cannot do calculations with percentages. All right. So got to take it as a number. So 1 minus 0.1 gave me that 0.9. So as you notice, B is a number that is less than 1. It is a decimal number. It is a fraction. 9/10 is the actual number. It's a fraction. All right. So for exponential decay, your B has to be less than 1. You know that B is greater than 0, right? So that means B is greater than 0 and B is less than 1. So it's a positive fraction that is less than 1. Okay, so B has to be between 0 and 1. So that's what makes it an exponential decay. So B is called the decay factor. Earlier it was the growth factor, right? This time it is my decay factor. So if I have to put all these things, so this is 1 minus R. So B is 1 minus R. If I have to put them all together, and I can rewrite my exponential function tailored to my exponential decay. So f of t is a times B is 1 minus R because I'm taking away from that 100%, right, to the power of t. So this makes it my exponential decay function. So this is my final value. This is my initial value. When I say value, it's a value of your y. All right. Initial value. This is the rate of decay, percentage written as a number. And this is my time period, the time that I allow it to decay. Or say if I want to find the value of the car after 20 years, what will be the value of the car after 20 years? Okay, so that kind of a thing. So this is exponential decay. All right, exponential decay function. So we can go over it in class, and also we will do some problems. Please watch the videos and take notes. See you in class. Bye.